Lecture 33. The Quantum Mind and Consciousness Paradox Introduction. Welcome to the threshold where reality itself becomes questionable. I'm speaking to you today about perhaps the most profound mystery in existence, consciousness, and its enigmatic potential relationship with the quantum realm. This is Lecture 33. The Quantum Mind and Consciousness Paradox. What if the very essence of your awareness, your sense of self, your innermost thoughts, arise not merely from classical neural firing patterns, but from quantum processes occurring in the microscopic structures of your brain? What if consciousness itself emerges from the shadowy domain where quantum uncertainty reigns? These questions haunt the boundaries between physics, neuroscience, and philosophy, opening doorways to perspectives both revolutionary and controversial. Today, we'll journey through several interconnected realms. First, the foundations of quantum physics, its strange and counterintuitive principles. Second, the enduring enigma of consciousness, what David Chalmers famously called the hard problem. Third, theories that propose quantum mechanisms underlying consciousness. Fourth, the orchestrated objective reduction theory, the most mathematically developed quantum theory of mind. Fifth, the criticisms and alternative perspectives. And finally, the profound philosophical implications these theories present. Our expedition requires both scientific rigor and philosophical openness. The territory ahead resists conventional mapping, demanding we question our most fundamental assumptions about reality itself. Foundations of quantum physics. To comprehend the quantum theories of mind, we must first enter the bewildering landscape of quantum physics, a realm where particles exist in multiple states simultaneously, where certainty dissolves into probability clouds, and where the act of observation itself shapes reality. Quantum mechanics emerged in the early 20th century when scientists discovered that, at the subatomic level, classical physics simply breaks down the orderly, predictable universe of Newton and Einstein fragments into a kaleidoscope of possibilities and paradoxes. Three quantum principles are particularly relevant to consciousness theories. First, superposition, the uncanny ability of quantum particles to exist in multiple states simultaneously. Unlike a classical bit that must be either 0 or 1, a quantum bit or qubit can exist as both 0 and 1 concurrently, only collapsing into a definite state when measured. Second, entanglement, what Einstein hauntingly called spooky action at a distance. When particles become entangled, their properties become correlated in ways that defy spatial separation. Measure one particle, and its entangled partner instantaneously reflects this measurement, regardless of the distance between them. Third, wave function collapse, the mysterious transition from quantum possibility to classical actuality. Before measurement, quantum systems exist as probability waves. After measurement, they manifest as definite particles with specific properties. These quantum phenomena have provoked profound interpretative debates. Does the wave function represent reality itself, or merely our knowledge of reality? Does consciousness play a role in collapsing the wave function, as suggested by the Copenhagen interpretation? Or do infinite parallel universes branch off with each quantum event, as proposed by the many worlds interpretation? Even more bewildering is the measurement problem, the question of what constitutes a measurement that collapses quantum possibilities into definite realities. Some theorists propose that consciousness itself might be this collapsing factor, a provocative idea that forms one pathway connecting quantum physics to the mind. What's crucial to understand is that quantum physics reveals a reality fundamentally different from our everyday experience, a reality where certainty dissolves into probability, where observation shapes what's observed, and where seemingly separate entities remain mysteriously connected. Consciousness. The hard problem. Before we can explore quantum theories of consciousness, we must confront the enigma of consciousness itself. Despite centuries of investigation, consciousness remains stubbornly resistant to scientific explanation. As philosopher David Chalmers eloquently framed it, there exists an explanatory gap between physical brain processes and subjective experience. We can map neural correlates of consciousness with increasing precision, yet this mapping fails to explain why these physical processes generate experience at all. Why does the activation of visual cortex give rise to the subjective experience of seeing red? Why does stimulation of nociceptors produce the feeling of pain? Why is there something it is like to be conscious at all? This is Chalmers' hard problem of consciousness, not merely explaining which neural processes correlate with consciousness, but explaining why and how any physical process could generate subjective experience. Classical neuroscience offers sophisticated models of information processing, neural networks, and brain dynamics. Yet these models remain fundamentally incapable of bridging the explanatory gap. How can electrochemical signals, however complex, transform into subjective experiences? This explanatory chasm has inspired some theorists to look beyond classical physics to the mysterious realm of quantum mechanics for potential solutions. Perhaps, they suggest, the key to consciousness lies not in classical neural activity, but in quantum processes occurring within neural structures. Quantum theories of consciousness, the quest to connect quantum physics and consciousness, has produced several distinct theoretical approaches. The first approach suggests consciousness emerges from quantum computing in the brain. Just as quantum computers can perform certain calculations exponentially faster than classical computers by exploiting superposition and entanglement, perhaps the brain utilizes similar quantum advantages. This perspective views consciousness as fundamentally computational, but operating on quantum rather than classical principles. Proponents argue quantum computation could explain the brain's remarkable efficiency, its pattern recognition capabilities, and the unified nature of conscious experience. Critics counter that the warm, wet environment of the brain would cause quantum effects to decohere far too quickly to support cognition. A second approach proposes consciousness plays a causal role in quantum mechanics itself. This perspective, associated with pioneers like Eugene Wigner and John Wheeler, suggests consciousness causes wave function collapse. In this view, the observer doesn't merely witness reality. The observer creates reality through the act of observation. This interpretation places consciousness at the very foundation of physical reality. It suggests a participatory universe where mind and matter are interdependent, rather than mind emerging from matter. Critics argue this approach risks introducing dualism and lacks experimental verification. A third approach focuses on quantum entanglement as a potential mechanism for binding the disparate elements of conscious experience into a unified whole. Our conscious experience isn't fragmented across brain regions, it's integrated into a seamless whole. Classical neuroscience struggles to explain this binding problem. How do distributed neural processes combine to create unified experiences? Quantum entanglement, with its capacity to create non-local correlations, offers a tantalizing potential solution. Perhaps widely separated neurons become quantum entangled, creating the unity of consciousness. However, maintaining quantum entanglement across macroscopic neural distances presents formidable technical challenges that many neuroscientists consider insurmountable. A fourth approach explores quantum effects in specific neural structures, particularly microtubules within neurons. Rather than proposing brain-wide quantum effects, this approach suggests quantum processes occur within these microscopic structures and somehow amplify to influence neural activity and generate consciousness. This approach, most fully developed in the Orchestrated Objective Reduction theory by Roger Penrose and Stuart Hameroff, deserves closer examination as perhaps the most mathematically rigorous quantum theory of consciousness. Penrose-Hameroff Orchestrated Objective Reduction, the Orchestrated Objective Reduction, OR, theory represents the most detailed quantum theory of consciousness, combining Penrose's mathematical physics with Hameroff's knowledge of neurobiology. Sir Roger Penrose, a mathematical physicist who shared the 2020 Nobel Prize in Physics for his work on black holes, approaches consciousness from a unique angle. He argues that human understanding, particularly mathematical insight, cannot be reduced to computational algorithms. Therefore, consciousness must involve non-computational quantum processes. Penrose proposes that quantum gravity effects cause objective reduction, or a non-computational collapse of the quantum wave function that isn't merely a result of observation, but an intrinsic feature of physical reality at the quantum gravitational scale. Stuart Hameroff, an anesthesiologist and consciousness researcher, suggested that microtubules, cylindrical protein structures that form the cytoskeleton of neurons, could provide the necessary quantum isolation to sustain quantum effects in the brain. Microtubules are composed of tubulin proteins that can exist in different conformational states. According to Orchestrated, these tubulin proteins can enter quantum superpositions. When enough tubulins enter superposition, a quantum gravity threshold is reached, triggering objective reduction and producing a moment of consciousness. The theory suggests that microtubules communicate with traditional neural activity through gap junctions, potentially altering neural firing patterns based on quantum computations and objective reductions occurring within the microtubule network. Orchestrated makes several concrete predictions. First, anesthetics work by inhibiting quantum processes in microtubules, not merely by affecting membrane receptors, a claim supported by evidence that many anesthetics bind directly to tubulin. Second, the theory predicts specific oscillation frequencies in microtubules corresponding to quantum processes, frequencies that have been partially verified in laboratory studies. Third, Orchestrated suggests that primitive forms of consciousness might exist in all systems with sufficient quantum coherence, potentially extending consciousness to simple organisms lacking brains. Intriguingly, recent experiments have shown quantum vibrations in microtubules at room temperature, lasting hundreds of times longer than expected, potentially addressing one of the main criticisms of the theory. Criticisms and alternative views despite its mathematical sophistication. Orchestrated and other quantum consciousness theories face substantial scientific criticism. The most significant challenge is quantum decoherence, the rapid destruction of quantum effects through interaction with the environment. Critics argue the warm, wet brain would cause quantum superpositions to decohere far too quickly to influence neural processing or consciousness. While Hameroff and colleagues suggest microtubules might provide quantum isolation, many physicists remain skeptical that quantum coherence could survive long enough in biological systems to influence consciousness. A second criticism focuses on scale mismatch. Quantum effects typically manifest at subatomic scales, while neural processes involve larger structures like synapses and neurons. Critics question how microscopic quantum phenomena could meaningfully influence the macroscopic processes associated with consciousness. Mainstream neuroscience generally favors classical explanations focusing on neural networks, oscillations, and information integration. Theories like global workspace theory, higher-order theories, and integrated information theory offer alternative frameworks for understanding consciousness without invoking quantum mechanics. Some philosophers further suggest that the hard problem might not require a quantum solution at all, but rather a conceptual revolution in how we understand the relationship between physical processes and phenomenal experience. Philosophical implications, regardless of their ultimate scientific validity. Quantum theories of consciousness raise profound philosophical questions about the nature of reality. If consciousness emerges from quantum processes, does this imply a form of panpsychism, the view that consciousness is fundamental and ubiquitous in the universe? Does quantum consciousness suggest that mind and matter are not separate substances, but different aspects of a more fundamental reality? Quantum theories also challenge our understanding of free will and agency. If quantum indeterminacy plays a role in consciousness, might this provide an opening for free will in an otherwise deterministic universe? Or does quantum randomness merely replace classical determinism without creating genuine freedom? The relationship between quantum physics and consciousness also raises questions about the nature of time and causality. Some interpretations suggest consciousness might exist outside linear time, forming a kind of atemporal background to experienced reality. Perhaps most provocatively, quantum theories of consciousness invite us to reconsider the relationship between observer and observed. If consciousness plays a role in collapsing wave functions, then consciousness doesn't merely perceive reality, it participates in creating reality. The implications of such participatory reality challenge our most basic assumptions about objectivity and truth. These philosophical implications extend far beyond academic curiosity, potentially transforming our understanding of ourselves and our place in the cosmos. They challenge us to reconsider what it means to be conscious beings in a quantum universe. Conclusion: we've traversed extraordinary territory, from the foundations of quantum physics to the enigma of consciousness, from theoretical proposals to philosophical implications. Where does this journey leave us? The quantum theories of mind remain speculative, awaiting further experimental validation. Yet they represent bold attempts to bridge physics and consciousness, matter and mind, objective and subjective. Perhaps their greatest value lies in challenging us to think beyond conventional boundaries. By connecting quantum physics and consciousness, these theories remind us that reality may be far stranger, far more unified, and far more mind-like than our everyday experience suggests. Whether or not quantum processes underlie consciousness, the quest to understand consciousness forces us to confront profound questions at the frontiers of science and philosophy. It compels us to recognize that the most intimate aspect of our existence, our conscious experience, remains the universe's deepest mystery. As physicist Sir Arthur Eddington wrote, "Something unknown is doing we don't know what." This humble acknowledgement of mystery may be the most honest stance as we continue exploring the quantum mind and consciousness paradox. Thank you for joining me on this journey through the labyrinth where quantum physics meets consciousness. In our next lecture, we'll explore another dimension of this mystery, the neural correlates of altered states of consciousness.